So the orbital diagrams just give us a little extra information. For hydrogen, it's that. Now, you may have seen the orbitals drawn as squares or just lines. That's fine. This electron is usually drawn on the left and pointing up, but it doesn't have to be. It can be, you can put the electron like that. It just has to be up or down. Nothing wrong with that either. It's just tradition. So, and you put only one S below. You don't put one S2 here or one S1 here. There's no need, because the arrows tell you everything that you need to know. Then lithium. 1, 2, 3. Then we have beryllium. Might have to use a couple of pieces of paper here. Boron. Now, if we have to go into another subshell, then you have to draw all of them. You can't just put 2p with one circle there. I mean, it's okay if you, in some instances, but for us, since we're just starting out, we want to draw everything here. Now, when we're finally to a point where we have a choice to make here. So you have an electron that we put into the p orbital. We could put it paired up, but electrons tend to try to get away from each other if possible. Since there's two openings, there's three openings actually. The electrons try to get will be in different orbitals, and they'll be pointing in the same direction. And then nitrogen. One, two, three, four, five, six, seven. It has 7 electrons. Note all of these are unpaired. That's what will happen until there's no other choice but to pair them up, and that's what comes next. 1, 2, 3, 4, 5, 6, 7. There's 8 electrons though, so now we have to pair them up. And we keep going along that line. Fluorine is one more electron that we add in. Has 9 total. 1, 2. See, we build up. 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice there's one opening left, and that's generally why fluorine only has one bond to it, because it only has one half-filled orbital for bonding. That will be later, but that's how we're going to start looking at bonding, is in terms of orbitals, and that's what these circles represent. Now the neon is completely full. All of the orbitals are full now. And then sodium, I'm going to have to, let me do it up here, just to have more room. Sodium requires us to go to the next level. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now notice I filled them up, half filled them, then went back. You might as well get into that habit. Because if you don't, if you just fill them, even though you know that these are all filled, you could fill this one, and this one, and then move on. It's better to get in the habit of half filling them. Leads to fewer mistakes. Okay, so, and also there should be a space in between each subshell. You should label each subshell. And there should be no superscripts here. That would be wrong, because you already have the information. You don't put 1s2, because we have 1s and it has 2 electrons in it. That tells us what we needed to know. Okay, write an orbital diagram for fluorine that goes against Hund's rule. Now Hund's rule is given somewhere. Wow, made quite a bit of progress through here. The lowest energy arrangement of electrons in a subshell is obtained by putting electrons into separate orbitals of the subshell with the same spin before pairing electrons. So I can write these a little bit larger this time. So we have so if we did that, and we say, so putting electrons in separate orbitals with the same spin before pairing. So if you did this, that would be wrong. That would go against Hund's rule. putting them like this first before you fill up these, that would go against Hund's rule. This would definitely go against Hund's rule, putting 3 electrons in there. So these are all possibilities that are wrong. The orbital diagram for technetium, and since I already did this out, if I'm lucky enough to find it, let's, this pile of stuff that I just thrown out, or just used. Amazing number of pages for that last one. So 1s, 2s, 2p, notice just one term under all of those p orbitals, 3s. So I should note that the reason that we have the orbital diagrams is that they give some more information. We can see the individual orbitals now, or representations of them. And they really gives us a better feel for the bonding and what's going on inside of the atom. So 1s, 2s, 2p, 3d, 4d. Okay, so these are all going to be filled. You can see that this would take a long time, so I'm not going to ask you to do too many of these on the exam. You'll probably get one that's fairly lengthy just to make sure that you can fill them up. And then also you can use the abbreviated, the noble gas core. And then the last thing is 1, 2, 3, 4, 5. Notice that all 5 are in different orbitals because they can be. According to Hund's rule, that's what we want. Okay, and then let's see. I ask you to do, yep. Now, bismuth. Yeah, that's another toughie here. So, wow. Yeah, let's do it out. I was gonna say let's skip it here, but no, let's just do it out. So 1s, 2s, 2p, 3s. Might as well give you some practice. I would really say to pause the video and try to do this yourself. Because if you can do this whole thing out and get them all right, then you are really doing fine. And then we have 5p, 6s, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. You can see how nasty it can get as we go along. This is 6p. So that's everybody, and so that's all of these get filled up. And this would definitely be the, oops, just follow my rule here, half fill them. But if you can do something like this on the exam, I don't think I'd give it this much. I usually stop after 30 or 40 electrons. But this is the reason I did this out, so you can see the 4f orbitals, because rarely do you see the orbital diagrams get to that point, but you might as well see it now. And then it's 6p3. Whoa, yeah, so not something you'd expect to see on the exam. That much detail, or that many electrons. Now silver, I'm going to just go with krypton, just to save time. So you can do out all the orbitals, and don't worry, I'll make it absolutely clear whether or not you can use the abbreviated form on the exam. For my exams, I tell you I want the full orbital diagram. I'll make a big point of it. This would be for silver. It ends with 5s2, 4d9. So, and then the orbital diagram for chromium, this one I want to write out completely because it's really a nice one to see why we shift that electron. Remember, this is the one has the, okay, 1s2, 2s2, 2p, 6, 3s2, 3, okay, 3p6, 4s2, and then 3d. Just wanted to get this right. And then chromium, I have this here. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. 1, 2, 3, 4. Now that's incorrect. As we know, it's 4s1, 3d5, but you can now have a better feel for what's going on here. We have this empty orbital in d orbital, and if we move this electron here, then we now have, instead of having 4 half-filled orbitals and 1 empty, now we have 6 that are half-filled. And it just turns out to be a lower energy state to have that that setup. So on the exam, if I gave this problem, that would be the whole point of having it. So even if the only thing you forget to do is change that electron over to here, it would be completely wrong, because that's why I have that problem on the exam. And then copper also has its own exception. Now, determine whether each of the following is paramagnetic or diamagnetic. So let me get my periodic table here. So actually, there's a shortcut, but first things first. Let me just write it out. Write out the orbital diagram. Anytime you have an unpaired electron, it is paramagnetic. If all of the electrons are paired up, diamagnetic. So this is paramagnetic. For neon, since we have more room, I'm going to draw these larger. Notice all of its electrons are paired up, which means that their magnetic fields cancel each other on the macroscopic level. They're definitely still there within the orbital, but they cancel each other, and we don't sense anything, any magnetic fields from them, so they're diamagnetic. Magnesium, one, two, boom, 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 boom. And then magnesium fills this level up, all filled up, so diamagnetic. And then sulfur, so it's 3, 1, 2, 3, so 1s, 2s, 2p, 3s, 3p. So all of these are filled. And if you want to use noble gas cores, well, the noble gases are definitely filled, so we could, right here, we could just put in neon and get the same information. So 1, 2, 3, 4. There's 1, 2, 3. Yeah. So there's unpaired electrons, so it's paramagnetic. Now, here's a shortcut for you. Notice that magnesium is at the end of the S block. So actually, everybody in this block would be diamagnetic. Everybody in this block would be paramagnetic. For this block, the only one that's filled is at the end. So these would be diamagnetic. Everybody else would be paramagnetic. Move down the line. The noble gases are on the end. These are diamagnetic. Everything else is paramagnetic. Could do the same thing for these as well. Rarely get into these, but this would be diamagnetic. Everybody else is paramagnetic. Recognizing that you're at the end of a block tells you that you're at the end of a subshell, which means all of the orbitals in that subshell are filled. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 elements that would be diamagnetic by their position in the periodic table. Everybody else is paramagnetic. Let me just verify, make sure I didn't miss anybody. Yep, and that's it.